Rain falls endlessly on Earth, beginning a storm that will reshape evolution forever. Imagine rain lasting not days, but nearly 2 million years. This is the Carnian Pluvial episode. This global transformation began 234 million years ago during the late Triassic. Before the rain, Earth was dominated by the massive supercontinent Pangaea. Surrounding it was Pangaea, the vast superocean encircling the globe. A smaller ocean, the Paleotethys, filled the eastern margins of Pangaea. Climate was harsh, scorching heat, widespread deserts, and brief extreme monsoon seasons. These mega monsoons formed because of extreme land-sea distribution on Pangaea. Their intensity was far greater than any monsoon observed on Earth today. Pangaea's interior remained nearly uninhabitable due to extreme dryness and heat. Central Pangaean mountains split the continent, intensifying climatic chaos. These massive mountains created giant rain shadows, drying regions even further. Despite chaos, life flourished along coasts and southern areas with milder climates. This period followed the Great Dying, so ecosystems were still recovering. New evolutionary experiments appeared constantly, including the earliest true dinosaurs. From Brazil's Santa Maria Formation came Staurikosaurus, one of the earliest dinosaurs. It measured only dog-sized, feeding on small reptiles and early synapsids. Another dinosaur, Reorganized, was tiny yet surprisingly carnivorous. Though meat-eating, Reorganized belonged to early sauropodomorphs, ancestors of giant herbivores. Numerous non-dinosaur dinosauriforms also roamed, like Lagosuchus and Marasuchus. These creatures looked like strange lizards, yet were close dinosaur relatives. Early archosaurs diversified. Phytosaurs, Aetosaurus, and Ravisuchians emerged. Marine life also changed, with early plecodons and belemnites evolving. Earth seemed stable, yet deep below, massive volcanic forces were awakening. Soon, the Pangaea eruptions would trigger climate chaos unlike anything before. Pangaea formed a giant volcanic province along western North America. These eruptions began releasing enormous volumes of basaltic lava. But more dangerous were the gases, massive bursts of carbon dioxide. CO2 rapidly accumulated, pushing global temperatures sharply upward. Some eruptions also released methane hydrates, far stronger than CO2. Methane accelerated warming dramatically, overwhelming Earth's climate systems. Rapid warming supercharged the hydrological cycle, transforming global rainfall. Storm systems expanded and intensified far beyond Triassic norms. Eventually, the sky darkened, and rain began falling relentlessly worldwide. This marked the beginning of the Carnian Pluvial episode, a world drenched in storms. Rain intensity skyrocketed, far exceeding anything in earlier Triassic climates. In some regions, rainfall eroded sediment so deeply it exposed basement rock. Floodplains expanded, and new inland megalakes formed across Pangaea. Humidity surged, transforming dry landscapes into humid swamp-like forests. Peat-forming wetlands returned for the first time since the Carboniferous. Yet the rain was not constant. Hyper-extreme precipitation came in violent episodes. Some areas, paradoxically, became even drier, especially deep inside Pangaea. These interior deserts were among the harshest environments in Earth's history. But worldwide, humidity dominated, reshaping ecosystems and flooding coastlines. Oceans changed too. Massive freshwater input began diluting global salinity. Lower salinity disrupted marine life, stressing animals dependent on stable salt levels. Carbonate platforms declined as ocean chemistry shifted rapidly. Major marine groups suffered. Conodons, ammonoids, and bryozoans declined sharply. On land, ecosystems destabilized as habitats transitioned abruptly into humid forests. Many herbivores struggled, especially rhynchosaurs, once dominant but now declining. Rhynchosaurs lost their preferred vegetation as forests shifted dramatically. Once abundant, they declined until only one family survived temporarily. Dicynodonts, long-lived synapsids, also suffered major losses during the event. Their diversity shrank, with many lineages disappearing entirely. Despite extinctions, other life forms saw opportunity in the humid world. Plants especially flourished. Humidity fueled explosive forest growth. Ferns and conifers spread rapidly, becoming dominant across vast regions. Bennetatailus also diversified, forming key components of Triassic flora. Expanding forests created new niches, favoring agile and adaptable animals. Early dinosaurs benefited greatly, increasing in number and diversity. Fossil sites grow richer after the rain, revealing many dinosaur species. The Ischigualasto Formation exemplifies this, containing at least 8 dinosaur types. Herrerasaurus dominated these forests, among the largest Triassic predators. It reached 6 meters long and wielded large, serrated teeth. Smaller dinosaurs like Eoraptor and Eodromeus hunted insects and small vertebrates. Sauropodomorphs also appeared, early ancestors of future giant sauropods. After the rains, their size and diversity expanded dramatically. Atosaurs thrived too, armored herbivores adapted to humid environments. Their bodies suited dense forests, letting them exploit new plant resources. Phytosaurs, crocodile-like but unrelated, exploded in diversity near wetlands. Rising water levels created vast habitats, perfect for these semi-aquatic hunters. Some phytosaurs grew enormous, rivaling future crocodilians in size. Crocodilomorphs and turtles also diversified after the humid shift. Many major Triassic predators, Ravisuchians, also expanded in size after the rains. New giants like Saurosuchus emerged, towering over most land animals. These predators ruled vast territories, dominating many late Triassic ecosystems. Yet even they felt the environmental upheaval triggered by the endless rains. Fossil records show many new Ravisuchian species appearing after the rainfall peak. Some grew larger, likely exploiting expanding prey and wetter habitats. Though powerful, Ravisuchians would eventually decline toward the end of the Triassic. For now, Earth was deep within the pluvial episode, its world reshaped by storms. Rainfall carved landscapes, forming canyons, ravines, and newly exposed rock layers. Sediments washed into oceans, altering chemical balances, crucial to marine life. Conodonts, fragile marine animals, were among the hardest hit. Ammonoids also suffered major losses as ocean conditions destabilized. Bryozoans declined too, unable to maintain their carbonate structures. This marine crisis formed a quiet but significant extinction pulse in the Triassic. Meanwhile, on land, shifting rainfall patterns forced animals to migrate or perish. Flooded plains replaced former drylands, reshaping herbivore feeding grounds. Some species adapted quickly, while others vanished entirely. The world's moisture supported vast, dark green forests across multiple continents. These forests allowed new plant groups to flourish beyond previous ranges. Dinosaurs thrived in these dense habitats, gaining evolutionary momentum. Increased humidity may have accelerated dinosaur growth and reproductive success. Many formations reveal sudden jumps in dinosaur abundance after the rainy period began. The pluvial episode indirectly set the stage for dinosaurs to dominate Earth. Ecosystems reorganized, forming new predator-prey relationships across Pangaea. Ancient wetlands became hotspots of evolution, hosting countless species. Even early mammals' ancestors adapted, finding refuge in humid forests. The world was changing fast, but the rains were far from over. Constant storms reshaped coastlines, creating new habitats and erasing old ones. Erosion transported minerals, enriching soils across newly formed floodplains. Richer soils fueled even greater plant expansion, locking Earth into a humid phase. Forests spread across continental interiors, once dominated by deserts. Rainfall filled massive basins, forming lakes potentially larger than modern Great Lakes. These inland seas altered wind patterns, further stabilizing humid climates. Across wetlands, insects flourished, becoming vital food for early dinosaurs. Amphibians expanded as well, thriving in countless new freshwater systems. But many aquatic reptiles faced stress as salinity shifts challenged their physiology. Marine ecosystems struggled to recover as storms constantly stirred sediment. Coral-like carbonate platforms collapsed, reducing habitats for countless marine species. Meanwhile, volcanic activity persisted intermittently, prolonging climate instability. Greenhouse gases kept Earth hot, making storms even more intense. Intense heat boosted evaporation, feeding moisture back into the atmosphere. This feedback loop helped sustain nearly 2 million years of rainfall. Yet rainfall was not uniform. Some regions cycled between wet and brief dry phases. Intermittent dryness allowed certain species to persist despite extreme conditions. But in the heart of Pangaea, dryness intensified, creating super deserts. These interior deserts represent some of the harshest climates in Earth's history. Life avoided these zones, clustering instead along coasts, lakes, and humid forests. Forests now served as evolutionary incubators, protecting species from climate extremes. Herbivores adapted to new vegetation, shifting diets toward ferns and conifers. Predators adapted too, refining hunting strategies for dense forest environments. As ecosystems reorganized, biodiversity climbed despite ongoing extinctions. Earth was becoming a greener, wetter world, but still unstable and unpredictable. Storm-driven rivers carved new channels, redirecting entire water systems. These shifting waterways reshaped migration routes for countless species. Wetlands expanded into former grasslands, forcing ecological restructuring. Animals that adapted quickly found abundant resources in these lush habitats. But specialists dependent on dry environments vanished from the fossil record. This transition marks a major, often overlooked extinction pulse on land. Rhinoceros, once dominant herbivores, dwindled to near extinction. Only one family briefly survived before disappearing in the next geologic stage. Dinosaurs survived longer but still faced severe ecological pressure. Their once diverse lineages vanished one by one as habitats transformed. With herbivore competitors fading, early dinosaurs gained ecological advantage. Fossils show increasing dinosaur dominance in many Carnian and early Norian sites. Their agility and adaptability made them well suited to humid, forested landscapes. Early sauropodomorphs grew larger as abundant plants fueled their evolution. Predatory dinosaurs refined hunting strategies in dense, wet environments. Meanwhile, phytosaurs exploited rising water levels better than most predators. Their crocodile-like snouts and aquatic skills made them apex wetland hunters. Atosaurs continued expanding. Armored herbivores adapted to soft, muddy terrain. Their heavy armor protected them from increasing numbers of predators. Crocodilomorphs diversified into small, swift terrestrial hunters. Some early turtles evolved unique shells, suited for marshy, flooded landscapes. Humid conditions also reshaped global atmospheric patterns and monsoon cycles. Mega monsoons grew stronger, influenced by vast new lakes and wetter continents. These storms redistributed heat across Pangaea, further stabilizing humid climates. Yet beneath this stability, ecosystems remained fragile and prone to rapid change. Global humidity encouraged rapid soil formation, accelerating forest expansion. Flooded valleys turned into rich ecosystems, supporting diverse animal life. These wetlands became long-lasting refuges for both predators and prey. Constant moisture allowed forests to grow denser than ever before in the Triassic. Such density favored agile species that could maneuver between thick vegetation. Small theropod-like carnivores refined silent stalking techniques in wet forests. Humidity muffled sound, giving predators more stealth in the undergrowth. Herbivores developed sturdier limbs to navigate muddy, slippery terrain. Increasing plant diversity meant new diets and evolutionary opportunities. Meanwhile, marine food chains struggled to reorganize after major die-offs. Algae populations fluctuated wildly as ocean chemistry remained unstable. Lower salinity challenged many marine reptiles, altering their global distribution. Only adaptable species persisted, shaping a new marine community. On land, increasing rainfall continued to alter river networks across continents. New river routes isolated populations, promoting speciation over generations. Isolation helped accelerate dinosaur diversification across Pangaea. Fossils show dinosaurs increasing not just in numbers, but in ecological roles. The Pluvial episode acted as a giant evolutionary filter, selecting adaptable species. Life reorganized, preparing unknowingly for the rise of future giant dinosaurs. Across continents, rainfall slowly began to lessen, but the world was transformed. As volcanic activity waned, CO2 levels began a gradual decline. With lower greenhouse gases, temperatures slowly stabilized. Storm intensity weakened, allowing ecosystems to settle into new equilibria. But the environmental changes were permanent. Earth would never return to its old state. This new world set the foundation for dinosaur dominance for the next 160 million years. As humidity persisted, plants continued diversifying across Pangaea's forests. Ferns, cycads, and conifers flourished, becoming global ecological pillars. These expansive forests supported complex food webs never seen before. As vegetation expanded, oxygen production increased, enriching the atmosphere. Some scientists suggest oxygen boosts may have aided vertebrate growth. Dinosaur lineages radiated quickly, filling ecological roles left open by extinctions. Their numbers surged, marking a major evolutionary shift in Earth's history. Soon after, the first giant sauropodomorphs appeared in the Norean. Species like Lesomsaurus reached lengths up to 12 meters. Though small compared to Jurassic giants, they were huge for their time. This rapid size increase may reflect abundant food and reduced competition. Atosaurs also diversified further, adapting to variable wet-dry cycles. Their armored bodies protected them, from emerging giant predators. Phytosaurs reach peak diversity, dominating freshwater ecosystems. Some species grew larger than crocodiles today, hunting even young dinosaurs. Their long, upward-facing nostrils allowed stealth breathing at the water's surface. But as environments stabilized, phytosaurs faced increasing ecological competition. Meanwhile, small mammal ancestors adapted further, thriving in dense forests. Their improved jaw muscles and teeth helped diversify their diets. These evolutionary innovations paved the way for true mammals millions of years later. Across Earth, ancient species disappeared, but new lineages flourished in their place. The result was a complete ecological restructuring unprecedented since the Permian. Forests, rivers, and wetlands created interconnected biomes across Pangaea. These networks supported extraordinary biodiversity that reshaped future evolution. Yet despite this flourishing life, the pluvial episode had not fully ended. Dinosaurs now occupied niches once dominated by ancient reptile groups. Their spread marked a major biological shift across Pangaea. Fossils reveal increased dinosaur abundance in formations across South America. Similar rises occurred in India, Europe, and parts of Africa. These patterns reflect a true evolutionary radiation, not just chance fossilization. As dinosaurs diversified, predators and herbivores alike grew more specialized. Some species evolved longer limbs for speed in dense forests. Others developed stronger jaws to process tough conifer vegetation. Predatory dinosaurs refined vision and balance to hunt in low light. Meanwhile, phytosaurs remained apex hunters along the world's inland lakes. Their long bodies and stealth approach made them nearly unbeatable ambush predators. But crocodilomorphs were evolving too, becoming faster and more versatile. These early crocodile relatives eventually challenged phytosaurs in many habitats. As climate stabilized, phytosaurs began losing their ecological advantage. Over millions of years, crocodilomorphs would outlast them entirely. Meanwhile, volcanic emissions finally declined, reducing atmospheric greenhouse gases. With less CO2, global temperatures slowly cooled. Rainfall weakened further, allowing seasons to become more predictable again. Flooded landscapes retreated, leaving behind fertile soils and new river systems. Wetlands dried into plains, while some mega lakes persisted for ages. Forests stabilized, becoming permanent features of many regions. These new ecosystems supported the evolutionary pathways of future giants. The world shifted from arid landscapes to humid forests, an irreversible transformation. The Carnian Pluvial episode ended, but its legacy lived on in every ecosystem. Without this rainfall event, dinosaurs might never have risen to global dominance. As the rains faded, Earth emerged transformed into a greener, richer planet. Ancient deserts gave way to forests and fertile floodplains. New rivers, lakes, and wetlands supported expanding biodiversity. Life reorganized, preparing the stage for future evolutionary success stories. Dinosaurs grew larger, stronger, and more dominant in this post-rain world. Without the ecological reshuffling caused by the rains, their rise might never have occurred. Crocodilomorphs also flourished, beginning a lineage that survives to this day. Early turtles adapted and persisted, eventually spreading across the globe. Many modern plant groups trace their roots to this humid evolutionary burst. The Carnian Pluvial episode thus reshaped not just landscapes but life itself. A forgotten extinction pulse quietly redirected the course of evolution. By removing old dominance, the event opened opportunities for new dynasties. Dinosaurs were among the greatest beneficiaries, rising from obscurity to prominence. Their dominance would shape the next 160 million years of Earth's story. Ecosystems born from rainfall became the foundation of the Mesozoic world. Even after the rains ended, their effects echoed across every ecosystem. Oceans stabilized slowly, forming new marine communities from surviving species. On land, forests persisted as permanent landscapes, replacing ancient arid regions. The global climate had shifted. Earth entered a new chapter in its history. What began as volcanic chaos ended as an evolutionary revolution. Today's ecosystems still reflect the outcomes of that ancient rainfall. Many modern lineages owe their existence to this 2-million-year storm. Without it, Earth's biodiversity might have taken an entirely different path. So the next time rain falls, remember the storm that shaped life on our planet. The Carnian Pluvial episode, 2 million years of rain that changed Earth forever.